Our next speaker is Hemley from the University of Illinois at Chicago, who will share his experience on synchrotron radiation and geoscience applications. So if you could please unmute yourself and share your screen.
Okay, thank you very much. Well, I'd like to thank the organizers for the opportunity to present this overview of the high pressure infrared program. I'm the spokesperson for a growing user community that I'd like to thank. And I also want to give special thanks to Xinjin Liu and Larry Carr, who have been partners in this effort. I've entitled this talk, Synchrotron Radiation and Geoscience from Terahertz to Gigayears, in such a bold way because we're talking about really 30 orders of magnitude in time scales when you think about the wavelength of the radiation we use and the kinds of problems we're dealing with concerned with the evolution of the Earth and even the solar system. I probably should have added giga electron volts to the title too, because we're using large accelerators with those energies. So what I'd like to do is give this overview with starting off with some background and context and really put this in my perspective in a way that I think it fits with our focus on the future and how these programs will evolve. Then give a short history of the evolution of the high pressure synchrotron IR program, which is a small part of the broader geoscience synchrotron effort. And I'd like to review some of that, give some selected highlights from NSLS2, the new FIS facility, and then a few comments on new opportunities. So beginning with the historical context, looking to the future, I think it's important to realize how we got here. So it was some 30 years ago that the idea of there being a successful and potentially very productive partnership of synchrotron radiation with geoscience, and in particular for dedicated facilities, emerged in the 1980s. And as mentioned or described in the opening page of this 1990 report, synchrotron radiation facilities were called out as a primary goal for new facilities in earth materials research. But leading to this really were the efforts of pioneers in the field, visionary scientists in different areas of geoscience that really set the stage during the late 1970s and early 80s. Bill Bassett at Cornell and of course Joe Smith at the University of Chicago, and that led to, even before this report, the original geoscience synchrotron user interest group called Geosync. And now, after a series of excellent reports, many from the National Academy, we have this new report that articulates the exciting challenges for the decade. And this was mentioned earlier a couple of times in the session. So of course, we're dealing with light sources. So that effort has led to the successful partnership with light sources. These are the principal ones that are stewarded and maintained by the Department of Energy in the United States. Most of our efforts in my group concern the X-ray region, but we've been very active in the infrared part of the spectrum for synchrotron radiation, and that's what I was asked to talk about today. So what about synchrotron radiation from terahertz to hard X-rays? Well, here we have curves showing brightness versus energy, showing the exciting prospects for the APS upgrade and other upgrades in the hard X-ray range. But in addition, there is, of course, at long wavelengths, at low energy, an important advantage of synchrotron radiation. And this nice figure put together by Larry Carr shows that with the NSLS2 large gap source that we have at the facility that I'll tell you about, we're talking about increasing the broadband spectrum to the equivalent of say, a 3 million Kelvin black body. So this is clearly something you cannot do and shows the value in part for synchrotron radiation in addition to its collimation and being able to work at a diffraction limit. So Infrared spectroscopy has been a unique tool over the years in Earth and planetary sciences, not a major component of the kinds of efforts we've been hearing about, but it tells us about thermodynamic properties, water and carbon storage content and mechanisms, structures of magmas, melts and glasses, phase transitions and bonding properties, and thermal and radiation conductivity or deep earth materials, and I'll give some examples of some of the breakthroughs. And the special advantages of the synchrotron infrared are really, as I mentioned, being able to work at the diffraction limit, which is key for looking at the small samples that we're all dealing with, trace amounts of material. There's high flux in the far infrared, so that's the real advantage in part of synchrotron IR relative to conventional source. It's also a pulse source, which I'll get to, and you can use this technique to study electronic properties as well. And this is a curve here of brightness versus frequency from NSLS, the facility that we use for most of what I'll be describing. So I want to give you a sense of the evolution of this program. And really this came together as a result of the pioneering efforts of Gwen Williams at NSLS, who approached us and said, we think there's a value in using synchrotron infrared for mineralogy, for geophysics, and for microspectroscopy in general, in particular in diamond cells. So we began the first experiments in the early 1990s. This led to dedicated beamlines for this science. And here we were helped greatly by Larry Carr at NSLS. And this emerged up through the compress era, and with the addition of Zhenjin Liu, who's been the sole beamline scientist at that facility who's managed this successful program ever since, including the successful transition to FIS, which I'll describe, and where first light was obtained in April 2019 and user experiments in May of that year. So, some highlights here from NSLS that I want to mention, because some of this was discussed earlier. First of all, the first observation of hydrogen uptake in a silicate perovskite in a very early study. Many studies of the metallization of hydrogen by several groups, mainly ours, and this work has continued to Soleil and other synchrotron sources. The discovery of ICE-10, which is a classic problem, I'll come back to this at the end. The first shockwave measurements at a synchrotron source were done on our facility at NSLS. Discovery of new polymorphs, including boron, the confirmation of the insulating phase of alkali metals. This was mentioned by Vitali early on. The discovery of dehydration melting of the lower mantle in a highly cited paper, and then studying novel deep earth materials like different types of carbonates with different coordination and very, very high pressures. So with the bringing together of this program with Compress in 2002, there was a huge growth in the program, which led to some of those discoveries. A large number of new users came on board. We were able to bring on new equipment, shown here to support that. And so by the time the NSLS shut down in September 30th, 2014, we had a unique world-class user facility, the only one in the world dedicated in this way, with an expanded footprint on the NSLS floor, up to 220 publications, a quite impressive user community from many institutions. Again, and this was all supported by a single on-site beamline scientist who made this work. So in the transition to NSLS2, with the shutdown of NSLS, this was, in a sense, a first-order transformation, partially reconstructive in the sense that it was an altogether new beamline, but we were able to move a lot of the fine equipment from the NSLS across the street to the new facility that was built and is now operational and doing great science. So some of the key parameters for the infrared and terahertz region at the NSLS2, and I'm grateful for to Larry Carr for providing some of this information. We have top-down injection. So beam current, not electron energy, is really what's key here. The low field dipole bending magnets are optimized for the far IR. We can extract the far IR light and go down to very long wavelengths. And it has extremely high stability. This was actually one of the big challenges when Williams got the idea of trying to access the infrared part of the spectrum at a synchrotron source. Most of them weren't stable enough. And now we have one that's 10 times more stable than any other facility. So this is going to enable a lot of new experiments, long time experiments, and so on. So here's another plot of brightness versus frequency showing the capabilities of the NSLS2 large gap source for FIS compared to a few others. It's also important to realize that we have this pulse structure that we can, for which we can do dynamics experiments. In fact, going back to, for example, the shockwave experiments that we did years ago in partnership with Sandia. This has not really been accessed or used at all for geoscience applications, but it's a great potential new instrument or capability for us. So here we have the facility going forward. The FIS is at beamline 22IR-1. It's shared with another one, MET, so half of the beam time goes to FIS. Because of the success of the NSLS program and the modest cost of building this in comparison to X-ray sources, the NSLS2 operations funds provided all of the construction money. So there's a wonderful windfall for our community. Compress, now in partnership with CDAC, which contributes some, funds the operations. It's the first operating IR beamline for general users, and it has 2 end stations with a lot of square footage for different kinds of experiments. And you can see here, there are actually 2 different end stations here for different kinds of experiments. One for diamond cell experiments of high PT, and another for imaging and other kinds of high pressure experiments. And our first user was Elizabeth Thompson, now assistant professor at the University of the South. So the beamline has been very successful, very productive so far. Here's just an eye chart showing some of the publications. There are others that are in press and submitted. And I want to point out that such a large number of them are in high impact journals due to the excellence of the community that's using this program. So I want to now just highlight a few of the successes. This is just a sampling. I wanted to start with this one, which is from Jackie Lee's group at the University of Michigan, led by student Feng Zhu, where they were using this infrared capability to look at dehydration of mantle transition zone silicates and found evidence for metallic iron really controlling the degree of dehydration of mantle transition zones and minerals. And this has implications for global hydration of silicates and metal saturation, showing they're incompatible in the deep earth. Another example is quite different, and this is connected to physics, but I wanted to show it because it shows the large, very successful collaboration across many institutions, many groups, and many facilities. And this is made possible by Compress and other organizations. This was led by a student at Northwestern, Ryan Klein, and here he was looking at a classic problem, pressure-induced magnetic order collapse, and a model system was Geoscience, shown here. It's a model Kagome lattice, and infrared spectroscopy, as well as the kinds of techniques you just heard about from Urshan, were used to constrain this transition. And it really was bringing together these different techniques, as well as bringing in theorists from the national labs, as well as academia, that made this possible. And this paper had quite a large impact in condensed matter physics and science more broadly. The next highlight I'd like to mention is beautiful work now taking us into planetary astronomy. This is work that was led by Dan Shem and Yongjae Lee, and combined both X-ray and infrared. And what was discovered here in this paper that was just published in Nature Astronomy was that there is enormous enhancement of MgO solubility in fluids that are representative of those found in icy planets, large planets, shown by this reaction here. So they found using infrared spectroscopy in combination with diffraction techniques, this chemical reaction led to high concentrations of magnesium in water, and this suggests that deep water on Neptune and Uranus may be magnesium rich through reactions like this shown here. Now, in the last highlight I want to mention, I'll turn to some work that we've done and come back to this classic problem of the symmetrization of ICE-10, which is an interesting problem. And this also dovetails nicely with the nice results that we heard from Vitali on X-ray diffraction, looking at similar problems. Here's a phase diagram of H2O along with planetary geotherms or adiabats, showing, of course, now the ICE-7 is a mineral on Earth. And also showing some of the metastable, very complex metastable transitions and boundaries at low pressure. So the question that we wanted to return to was that looking at this transition at from ICE-7 to ICE-10, this symmetrization transition, I want to point out that, that this transition was actually predicted by Cam and Davis in 1964. Barclay Cam was actually the son-in-law of Linus Pauling, and this paper is not widely cited. He was the first to suggest that if you just compress ICE-7 far enough, you could reach a point where there could be symmetrization of the hydrogen bonds, and we found the first evidence for that from infrared spectroscopy. There have been continuing questions about this. For example, the mechanism of this. Are there intermediate phases? Are there quantum effects? Because it's a highly quantum system being hydrogen rich. And even after this work in the mid-1990s, at least 100 papers have been written on this transition and related transitions in ice, as well as some of the other transitions, such as the transition to the superionic phase that was mentioned earlier. So we've gone back to this problem recently. We actually studied it in U2A as well. These are the data that we obtained back in 1996. Beautiful pioneering measurements led by Alex Goncharov. We were able to get above 200 GPa and measure reflectivity and saw striking changes in the spectrum. However, we weren't able to access the far infrared. On the other hand, this prompted theory to come along and try to reproduce what we found. And they predicted, in fact, at low energy, at long wavelengths, an enormous increase in intensity of this band here, which we weren't able to see. And this arises from tunneling or proton disorder associated with the transition. So we've gone back to this, first of all, at U2A before the shutdown, and obtained the first far infrared measurements at megabar pressure for any material. And we obtained data like this up to 95 GPa. Saw features here at the highest pressures that we didn't quite understand. We've gone back to this at FIS and found much cleaner spectra. So now we can measure quite clean spectra at these high pressures, and at the highest pressures are quite different. Here's another comparison showing the kinds of data we've got at U2A with a much cleaner data we can get at FIS. And this is leading to a more interesting low temperature phase diagram. This is work in progress. And it's also notable that there are still major disagreements with theory. So this continues to be an important testing ground for theory, both theory applied to planetary modeling as well as to condensed matter physics. So in the last slide here, before the conclusions, I just want to point to some new opportunities where we can take some of the techniques that we've developed for high pressure studies, micro-infrared spectroscopy, and apply them to other areas. So first, starting with the planetary astronomy perspective, building on what I just described, of course, there's the excitement of looking at other Earths, super Earths, and other planets. And here there's a need to look for IR signatures of novel phases. We can do laboratory planetary astronomy to look for those materials, as well as the important question of biosignatures that might emerge from various kinds of astronomical observations. Another is extending this to geobiology and biogeochemistry at modest pressures or near ambient. And here we can do in situ IR imaging of life and components of processing of organic matter in extreme environments. This has basically not been done, but perfectly doable with existing techniques. And then extending this to other areas of geochemistry, looking at questions associated with the critical zone, critical minerals or materials, in situ IR imaging of speciation in fluids, reactions in complex assemblages and environments, and so on, taking advantage of the diffraction limit we can reach and be able to produce infrared maps of complex materials. And much of this dovetails beautifully with the kinds of recommendations and science priorities that are identified in Earth in Time, which again is an update on the much earlier NAS report. So just to conclude, NSLS-2 FIS is a unique world-leading synchrotron infrared facility for optical studies of materials in extremes. We had our first light in operations in April and May of 2019. Its unique features include the high beam current and exceptional stability, the space we have for integrating complex in situ variable PT experiments, including doing near infrared near focal infrared imaging and near field imaging altogether that were not being done at that facility. Also, the capabilities at FIS provide new opportunities for supporting X-ray experiments. We're already supporting X-ray diamond cell experiments with our quite ample sample prep and offline characterization lab for that. And we've been doing that for the X-ray DAC community at NSLS since the late 1980s. There's also this opportunity to open a second port, which would double the beam time for compressed users and for these kinds of experiments. And as I tried to point out, there are numerous problems to address in geoscience, defined very broadly, as well as in allied fields. And I want to give this now an opportunity to thank the principal sponsors of this effort, Compress, and the partnership with NSLS2, and the support also we get from the NNSA through CDEC. And I thank you for your attention and take any questions.
Thank you, Ras, for sharing these breakthroughs of synchrotron infrared and terahertz research that is done at NSLS. If you have any questions, please raise your hand and or type in the chat.
Afu had questions.
I thought give his congratulations.
Okay. Can I ask questions?
Yeah, sure.
Ross, very good talk. And it's definitely a great opportunity, especially for the diamond cell, to use a synchrotron infrared. Maybe I miss, what's the focal spots that smallest we can do? Can you do a mapping within the diamond cell? Is it feasible or not?
Yes, and so for people who don't think about the infrared and work in the X-ray region, we have a diffraction limit to work with. Yes. So it all depends on the wavelength of light that you are dealing with. So if you want to get down to 1 micron imaging, 2 micron imaging, then that's sort of the wavelength cutoff in broad terms for the mapping. If you're working at shorter wavelengths, then it increases. But so you can produce maps, at the micron scale. So we're not talking about submicron because at least for the standard kinds of far field work we do, that's the limit. If you go to the near field, it's entirely different. That's not being done in this program for high pressure, but is something that we would like to develop. It's something that has been used extensively at ALS, and I think there's an opportunity to do more of that in our facility for geoscience as well.
Mm-hmm. And you mentioned about the eyes that you're doing, but it was in cryo temperature and cryostat. Do you plan to do it at high temperature with CO2 laser heating?
Oh yeah, there's still a lot more to do. This was basically done at room temperature and some at lower temperatures, but yeah, there's still a lot more to do. It's amazing how many questions continue to persist regarding.
And what is the status of laser heating?
Pardon?
What is the status CO2 laser heating?
We have a CO2 laser heating apparatus, part of the beamline. That's been used less for in situ measurements, but is a tool that we have for users.
Okay, thanks.
Thank you. We have a question from Nanat. If you could please unmute yourself.
Yes, actually a comment. Nice talk, Russ, first of all, but I just wanted to comment to what you answered to Vitaly from experience. One of the advantages of the Synchrotron IR was the fact that when we're doing measurements, you can take measurements of the background and subtract at each point. Like in-house source, you're taking the spectra and the background is constantly there. So if you want to get a much nicer spectra, to the ability to actually take the background, subtract it. To me, that was the huge advantage. I don't know if necessarily, we were able to map out if we got that kind of resolution, but the fact that we were able to always subtract background at each pressure and temperature point. So yeah.
That's right. And of course, there's also the opportunity for a combined IR and X-ray experiments. We were doing more of that in the past, where users could come and do experiments on both beamlines, or X-ray beamlines, as well as ours. And there's an opportunity for us to further support the user community that will be moving elsewhere during the dark period of APS, for example. That was mentioned in the context of ALS. So we're stepping up to support users and help out in the X-ray area as well.
And you mentioned that you have quite a bit of space. Do you plan to have a nice high resolution Raman system to benefit infrared spectroscopy?
Oh, we have a Raman system. Yeah, I should have mentioned it's a fully integrated optical system. It's not quite like the one you have at Geoscience. It was built earlier, but I failed to mention that it's a general optical system, optical laboratory. So we have the ability to do Raman, to do all kinds of laser spectroscopy, as well as take beam from the source, from the synchrotron source, and do infrared in combination with the conventional source. So it's a general purpose micro optical laboratory.
Sounds good. Great, thanks.